Hi, we are Group 3, formed by Nicolás Pedraza, Juan, Camilo, Ordoñez, and Paola Medina. And this is our report for the fifth practice that is called Diffusivity of a Mosquito Repellent. First of all, for introduce our subject, we are gonna explain what is diffusivity. This property refers to the ease with which molecules of a solid move in a medium. But it is also important to explain what is a repellent and what its function and the relation that it has with diffusivity. First of all, a repellent is a volatile chemical substance which makes mosquitoes get away from humans, and its efficiency is determined by the diffusion coefficient. This property can change based on the steam pressure and the boiling point of the repellent, and as said, it affects the efficacy of the repellent against mosquitoes. That's why the objective of this practice is to develop a protocol to determine the temperature effect on the diffusivity of a mosquito repellent.
Now let's continue with the methodology. For the proposed methodology, we are going to use the novel open-top evaporation method. In this method, we measure the mass along time with the balance in the tube, as we can see in the image. For our proposed materials for our proposed methodology are first the diffusion tube. Why we don't use the traditional method? In our case, was a combination between eucalyptus and water. In this case, instead of measure, and finally the diminution of volume in the volatile liquid, the materials we are going to measure the mass are of the first the diffusion tube, volatile liquid, a repellent a long time. In our case, was a combination between eucalyptus and water. Is a balance, the structure, and finally a thermocouple. These are the steps that we need to follow in order to deliver our proposed methodology. First, we need to ubicate the tube and the balance, and then we need to turn the balance. Juan suggests us that the measure of the tubes need to be 1.49 centimeters for area and 12.6 centimeters for length. Then we need to fill the tube with the repellent, and then we need to measure the length of the tube that the repellent fills. This is very important because depending on the length, we are going to see if the repellent is diffusing or not. Continuing with the steps for the proposed methodology, then we need to start taking the time depending on the case. Juan suggests us that we can use a time between 10 minutes and 100 minutes. Then we need to start obtaining the data by intervals of time of 5 minutes. That's what Juan says. Finally, we need to repeat this process. We need to repeat the whole process, but with different temperatures in order to demonstrate that the temperature also have a really important effect on the diffusion. After the practice for our proposed methodology, with all the data, then we need to simplify the question in order to obtain the diffusion factor. Then with the diffusion factor, we need to graph all of these points and then use a linear regression in order to obtain like a summarize of the diffusion factor, depending on every temperature. Now this is the methodology that we use in order to obtain the diffusion. First, we identified every jar that we use because we are going to use different temperatures for the water that in our case were 10, 30, 60, and 90. Then we add 30 milliliters of water in every jar, and it's necessary that every jar have the water at each temperature, and then we add colorant to the mosquito repellent. In our case, we use blue colorant, and it's necessary to use in order to see the diffusion. Now that we have the water in our jars, we need to define the distance in order to take the data. In our case, we define a distance of 4 centimeters and we put a mark over there. Then we add 3 milliliters of the mosquito repellent into the water. We need to add 3 milliliters of mosquito repellent, no more and not less, because there was a relation 1:10 between the water that we add and the mosquito repellent we also add. Then we define the delta T in order to take the data. This delta t was 1 minute per 4 minutes. And then we analyzed the data with an UAVs. This equipment is an equipment that we use in order to obtain the observance and the wavelength of the substance that we are analyzing. That in this case it is the data that we obtain in the whole taking of data that was 4 minutes. After we obtain all the data, we need to now start delivering the mathematical part. For this, we need to first plot the observance versus the wavelength. This value is necessary to be plotted for each measure of data of and every temperature. And we need to plot this data in order to obtain the peak of the graph. Then we need to obtain the value of concentration in every point of the data. How we obtain this value? Well, with the peak that we already find, we in the graph, we need to use the Beer-Lambert's law to obtain the concentration. The Beer-Lambert's law is the one that is shown in the image. Here now we need to use the sorted equation. Here we can see the whole equation, the whole sorted equation. But in this case, we need to simplify it. We omit three terms. The first one is the velocity term that we omit because we assume that the jar is in a steady state. The second one is the same is we omit it because we assume that we have the same temperature inside the jar all the time. And finally, we omit the last term because we assume that there is no temperature change between the water and the mosquito repellent. Finally, we plot the diffusion coefficient that we found using sorted equation for every data that we use versus concentration in order to have a linear graph that we found the slope in order to find the diffusion factor, the overall diffusion factor for every temperature. Finally, when we found the diffusion factor, we plot diffusion coefficient versus temperature in order to see the behavior of the graph. That was the diffusion factor between temperature. If we compare methodology 1 between methodology 2, we can say that in the first one it is easier because in order to obtain data, we can spend a long amount of time. But in methodology 2, we can obtain more accurate data, but it is necessary to take in mind that we simplify factors that could affect the result, more specifically in the sorted equation.
Now we're going to present to you the results and analysis for this practice. The samples that were taken in the practice were also analyzed with a spectrophotometer, and the data collected from it was converted into these graphs that represent observance versus wavelength for each time that the sample was taken. These ones are for the system at 10 Celsius degrees. And we can see that in every graph, there is a tendency around 650 nanometers in wavelength, where the observance is the maximum observance. And this is the point that we're going to analyze later. Here are the same graphs for the system at 30 Celsius degrees, and we can see that there is a similar tendency here. These are for the one at 60 Celsius degrees. We can see again that the tendency is similar and also the values of the graphs. And finally, these are the graphs for the system at 90 Celsius degrees, and we can see that the tendency is still the same. Now, in order to obtain the concentrations for each system, we're going to use the Beer-Lambert's law, that is essentially this equation: observance equals molar absorption coefficient times concentration times length. In this case, this length is the distance through which light passes in the spectrophotometer, and that's why we have here the table 1 that has the constant values that are going to be used in this calculus. In this case, the length is always 1 centimeter. And also we have here the wavelength that is 635 nanometers. That is the wavelength at which the absorbance is the maximum absorbance in every graph that we already presented to you. And also we have here the molar absorption coefficient that is 89. In this case, this value is specifically for the wavelength of 635. And this one is for the acetic acid, even though our repellent was made essentially from water. But the molar absorption coefficient for water isn't accessible in literature, so we're going to use this one because of the similarities, and also the acetic acid is commonly used as repellent. And we are going to take this value as a base of calculus, and even though there is not the same value of the water, the tendency that we're going to obtain from this data is going to be the same. Here we present the different tables of data from each system. First, we have the samples, then the time at which those samples were taken, and the maximum absorbance for each sample. In every case, the corresponding wavelength is 635, that were the value that I already gave to you. And finally, for each maximum absorbance, we obtain the corresponding concentration using the Beer-Lambert's law. And here we have the four concentrations for the first system, for the system at 30 Celsius degrees, the concentrations for the system at 60 Celsius degrees, and finally the concentrations for the system at 90 Celsius degrees. Now that we have the concentrations, we finally can obtain the diffusion coefficient for each system using the Soret's equation, but in a simplified way. In this case, we can see how the simplification made the equation in this slide. And these simplifications are because of we assume the system as a steady state, and also that there is no temperature gradient inside the fluid. We also say that the coordinate system is Cartesian, even though the cylindrical coordinates are more suitable in this case because of the geometry of the recipient of the fluid. But again, this is for simplification. So we can say that the system has a unidirectional movement. Also, there is a simplification in which we use deltas instead of derivatives, as we can see in this equation. And for all these reasons of simplification, we can't actually use the Fick's law in this case in order to obtain the diffusion coefficient. And finally, we have the table 5, in which we present the constant values that are going to be useful for this calculus. First, we have the temperature of the ambient, that is 18 Celsius degrees, the initial position, that is 0 centimeters, and the final position, that is 1.6 centimeters. And this is the position where we took the samples. From these mathematical procedures that we followed using the Soret's equation, we can obtain a different diffusion coefficient for each delta in concentration. So here we present to you this data converted into graphs about diffusion coefficient versus delta concentration. And we can see that in each case, in each system, we can see a similar tendency or a linear tendency exactly. And here we have the same graphs for the system at 60 degrees and the system at 90 degrees. We can conclude from this linear tendency that in fact the diffusion coefficient increases as the delta in concentration increases too. But we can see in these graphs, and also in the ones that were presented before, that there is some values in the negative space, but this is something that we're going to analyze later in the video. On the other hand, we can also obtain only one diffusion coefficient for each system if we use the Surratt's equation, but doing the difference or the delta between the last and the first value instead of doing it in every pass of the time. So here in table 6, we present the results for the diffusion coefficients, and we can see that there are even some negative values, even though we know that the diffusion coefficient should increase as the temperature increases. We can say from this that these different values are because of the value of the molar absorption coefficient that we use that was for acetic acid instead of water, or there was actually a lot of simplifications in this calculus. So it is actually not surprising that the values are a bit uh, away from the reality. But we can say that there is a lot of maybe human error in the practice, or just in the mathematical procedures. And finally, we present here in a graph the last data that I already explained to you in a diffusion coefficient versus temperature graph. From this one, we can say, or we could say, that the diffusivity decreases as the temperature increases. But that is a conclusion that is not accurate, and that just remarks the errors in this practice, uh, maybe in the actual practice or in the mathematical procedures that we already explained. And so these are our results.
In, as a conclusion, we can say that in terms of the objective, we demonstrate that there is an effect on the diffusion if we change the temperature, as we already said in the analysis. Also, we can say that in order to obtain the diffusion coefficient of the mosquito repellent, methodology is better used because it has more steps, but depending on these steps, we can obtain more precise data. Also, we can say that in terms of results, the data that we obtained was not the best compared to the literature because it was very different. And as a final conclusion, we can say that for next studies, it's important first use two different methodologies in the lab in order to obtain more data and compare between those two methodologies, and also check more information in order to obtain coherent data, because that was one of the problems. We don't obtain data that was coherent.
Here are the reference that we used for this practice. Have a good day.